I received some emails from the students. So it seems that some of you have not got yet the concept of span clear, and that's good because I mean, if you write to me exactly where you are stuck, then I can go over it and clear it, right? So, yeah, please write down. What is a span? Well, we defined it to be linear combination of, given a finite set, it's just a linear combination of the, you are taking the set of all linear combinations of that, right? Let's redefine it once more. So suppose V is a vector space over some field F, okay? And suppose S is some subset of V. Okay. So by span of S will mean that put 0 there already, okay? And take the union of all the linear combinations of the form Ci, Vi, I running from 1 to n, such that Ci's are in F. Well, at first, what is n? So n is some natural number in n. That means it's not fixed which n you are taking, because S, you don't know whether it's finite or infinite. It just means that you are taking some finite linear combination. Okay. And then Ci's are in F, and Vi's are in V. Not V, excuse me. Vi's are in S. Okay. So we are taking all finite linear combinations of the elements of S. Rishit, any doubts? Because this will take care of the convention that we have made in the last class. Because take this empty set then. This one is empty. Here you have 0. Okay. Now, let's get back to the question of Bishesh. Where is Bishesh? Yeah. So you wondered why it is why we are only considering finite linear combinations, right? You asked in the last class why we are considering only finite linear combination. What is the problem with the infinite? Okay. So yeah, Mahfuz asked. Thank you. So yeah, then can you explain why not? Yeah. You haven't asked. Well, Mahfuz said that he asked, but do you have the answer to this? Yeah, that's an answer if you are talking about, say, reals. But in general, what does it mean to have an infinite sum? Well, let's go back to the definition of vector space, right? How we defined it? It had two things. One is that it's an abelian group, right? And the second was that if it is defined over some field F, then scalar multiplication with elements of F. By elements of F, right? And it satisfied three properties. That is, you require associativity, identity, that is, if you multiply with the identity element, you just get back the element, whatever element you are having in the vector space V, and then distributivity. That is, scalar multiplication is distributive over multiplication in the field as well as, scalar multiplication is distributive over addition in the field as well as addition in the vector space. Okay. So now when you are considering such a sum, and if the sum is not finite, what does it mean? So at first, suppose you are considering an arbitrary sum, Ci, Vi. Okay. Now, note that the Ci's are in F, and Vi's are elements in the given set S. Okay. So in particular, elements in that set is a subset of the vector space. So Ci, Vi in particular, all of these are inside your vector space V. Okay. Now we are taking the sum. So what property we are using? We are using the fact that it's an abelian group. Okay. Now what does an abelian group? What was the axioms of abelian group? If A is in V, B is in V, then A plus B should also be in V. It's a binary operation under which V is closed, right? Well, this then implies that if you take any finite linear combination, that belongs to V. How about infinite linear combinations? Okay. So for example, take R, the most familiar case, so the reals, and suppose you consider the sum 1 plus 1 plus 1 plus dot 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 dot. Yeah. So as you mentioned, this doesn't converge. I mean, we do not assign any value in R to this sum, because this, well, this is an abelian group R, and that means if you add 2 elements in R, you get an element in R back. If you add n elements from R in some finite number, you get an element in R. It doesn't mean that if you add infinitely many elements from R, you will necessarily get an element in R. Okay. So is there any way to remedy this? I mean, what is the remedy to this one? Yeah? Monideep? Yes, but suppose you want to make a space for this one, or for divergent series as well. So what should you do? Okay, at least put some value like infinity, say. Okay. And then the question becomes, this set, which you, I mean, minus infinity, you put there as where the things going, I mean, where all the sequences whose terms are increasing to, well, these are series actually. So have you done already, I mean, started series and sequences in analysis? Okay. All right, but are you familiar with this notation at all? Okay. So suppose you adjoin these two things and say that any such series which diverges to infinity, we say we give the value infinity to that sum. Okay. Will that work? So the question is that is this means this one, an abelian group so the yeah. Yes. 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 Right. Exactly. That's there would be sequences which are oscillating, okay, which are not converging to a particular point. At first, that's a problem. Secondly, this one, I mean, even if you define some other operation, then you will have, I mean, the general rule would be take any finite number, add infinity to it, and you will get back infinity. Okay. I mean, if you want to make it compatible with the addition in R. And the same thing happens with this one, right? Now, what is the candidate for additive inverse of this one? I mean, if it has to be at all an abelian group? Yes, and is this an additive inverse? Why not? Why? It will, I mean, it will violate the axiom of associativity. So you got this, right? And then consider this one. Okay. If this was 0, then it would be A. However, A plus infinity should be infinity, right? And that would give you 0. Okay. So this, so if this were an abelian group, the axiom of associativity would be violated. So thus we get a contradiction and hence this cannot be an abelian group. In other words, we cannot talk about infinite sums in any arbitrary vector space. Okay, and that's why we stick to only finite linear combination. Okay, so we define the span of a set as 0 union any finite linear combination. Okay, in particular now, if you take the empty set, you just get 0 there. Then in the last class we reduced spanning set to a basis, right? And there we assumed that the vector space is finite dimensional. So every finite dimensional vector space, if there exists a spanning set, it should have a basis, we saw. But we started with a finite spanning set, right? And then we reduced it. What happens if we start with an infinite spanning set? You are still given the vector space to be finite, but nevertheless, sorry, not finite, finite dimensional. Now, finite dimensional means that there exists some finite spanning set, but your set, which you are starting with, suppose that is not finite. What do we do then? Reduction of spanning set of a finite dimensional vector space to a basis. Okay, let's revisit this once. Okay. So suppose V is finite dimensional. Okay. Okay. And suppose is a spanning set for V. Okay. And we don't know whether S is finite or infinite. S is an arbitrary spanning set. We would like to see whether there exists a basis inside S. Okay. So whether we can discard elements from S and still get a basis. So we saw what we should do if the set is finite. Now, what's the idea? What should we do in the infinite dimensional case? Your name? Devanshu. Yes. So, can you just suggest some idea how should we proceed? We have a spanning set. Suppose S is a given spanning set and V is a finite dimensional vector space. Okay. Yes. How should we?
Eliminating those vectors which are independent.
Yeah. Finally, we need it to be linearly independent. But at the beginning, you just know that this spans V. That is, every element in V could be written as a finite linear combination of the elements of S. S could be infinite. S could be uncountable even.
We could eliminate those elements
which are not needed. Now, how do we figure out the elements which are not needed? Remember, we are given this fact that V is finite dimensional. Can we use this information to reduce? I mean, to remove all the elements which are not needed, which are redundant. I mean, without which we can still do. just 1 minute. What's your name? Yeah. Alhan. So what does a finite dimensional vector space mean, Alhan? Not a basis, but a. That's right. That's the definition of dimension. We have not given it yet. So till now, by a finite dimensional vector space, we just mean that it has a finite spanning set. Okay. So finite dimensional vector space. This means that it has a finite spanning set. Okay. Some finite spanning set may not be equal to that S. Okay. So give it some other name, say script S. Okay. This is that spanning set. Okay. Finite spanning set of V. So yeah, excuse me. What's your name? Yeah, Herman. So Herman, we would like to connect this S with this S, that S. Okay, and we know that this set is finite. We are not reducing this one to a basis. We would like to reduce that one to a basis. Okay. How should we proceed? Okay. This one, suppose this is a finite set, so you can give it a name, say W1 dot 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 Wm. Okay. Suppose that is this. We have not said it's an ordered set, so maybe we just write this one. Okay. So suppose this is your S. And you would like to relate this S with that S. What should we do? Herman? Same property, of course. Both are spanning V. But this is finite and you do not know anything about the cardinality of that. Yes? Which one? This one or that one? You have two spanning sets. Yeah? All right, yeah. Okay. But if you keep on going like this, then this is an infinite algorithm, right? So it may not halt. We require that. We know V is a finite dimensional vector space. That's right. Okay. Yeah. So you see, this is R2. You remove the span of this. You are still in this set. Okay. Now, removing the span would remove also 0, so you cannot remove 0. But suppose you remove everything else except 0. Then you remove this one. Then you remove this one. Then you remove this one, and keep on removing. Okay. You will never exhaust all the vectors. Okay. So, yeah, a more structured argument. Every linearly independent subset. Yes. Sure. Nice. That's of course a very good. That's definitely a way to proceed. But what we are trying to do here, we are trying to reduce this S to a finite spanning set. Okay. So we are trying to, as Alhan said, no, Devanshu said, I guess. No, both said actually, that we should reduce this one to some set after removing all the redundant elements. So we are proceeding in this manner. Nevertheless, what you said is perfectly okay. That can be done. Okay. Every element of that is. Of course, yes. Then. But these are auxiliary. You do not. I mean, you know that some of this exists. Some such set exists. So except, I mean, instead of removing elements from here, what you will do, let's, yes, right, very good, wonderful. That's what I wanted to, that's what we wanted to hear. So that is, these are the elements, okay, Alhan. So what we are doing is that we are considering W1 to Wm. We are expressing each of these W1 to Wm as linear combinations of elements from that set S. Okay. So suppose S is some infinite set. Okay, V lambda in some capital lambda. Okay, and you don't know what is the coordinate of this capital lambda, but you know that each of these Wi is some finite linear combination of these V lambdas. Okay, so this Wi say is sum over say C1 Cij Vj. Okay, j running from 1 to okay V some I mean not that. So you know that this is these are indexed by lambda. So some subsequence or some subset of this lambda. So some lambda j say, where j is running from 1 to n. Yeah, 1 to r, some finite linear combination as we said. Okay. So what we are writing, what we are doing is that we are expressing each element of this set as a linear combination of the elements in that set S. Okay, Herman, is it fine? Now what will it mean? So for each of these elements, you are getting a finite collection of elements in S, of which this is a linear combination. Now if you take the union of all such things which are expressing the elements of this set, that's also finite set, right? Because we are taking finite union of finite sets. Okay. So what I want to say is that for every okay, wait a minute, Cij V lambda j. Okay, but it would also be nice to write an I here, and there are too many subscripts. Very sorry about that, but this I should also be kept. I mean, this I is fixed because you are having this Wi here. So this I and this I are fixed, whereas j is varying from 1 to r. Okay, and then we are collecting all these V lambda i's for every I. Okay, V lambda ij's. So then what you are doing for every Wi, you are defining another set, say epsilon I, and what are the elements of epsilon I? This V lambda ij's. Okay, where I is fixed because Wi, I mean you are writing Wi as a linear combination of these ones, but j is running from over some finite set, j from 1 to r. Okay, and this r may also depend on I. This r may not be a fixed number. Okay, so maybe this is some ri. Okay, all right. What we are doing is that we are collecting all the vectors of S of which Wi is a linear combination. Is this point clear to all of you? Please let me know, otherwise we can go over this again. Yes, so where are you stuck, please? This one at first? Okay, so thank you very much. Your name? Nitesh. Okay, thank you, Nitesh. So this is a spanning set. Okay, what does a spanning set mean? You can write every element of V as a finite linear combination of the elements of S. Now here you have these elements W1 to Wm. Okay, it's a finite dimensional vector space, so it should have a finite spanning set. It may not be that one, but it is some other spanning set, W1 to Wm. What you are doing, you are taking every element here and you are writing it as a linear combination of the elements from this set. Okay. So this W1, for example, if you take W1 here, W1 is some linear combination of this V lambda 1j. Okay. Lambda 1j is, I mean, j is varying from 1 to r1. So some subset of the elements of, I mean, some elements of S, some finite set of elements of S. Okay. and that we are denoting by this E1. Okay. So E1 for W1. What E1 consists? It consists of all the elements in S whose linear combination is not all the elements. I mean, a set of finitely many elements in S whose linear combination is giving you W1. Okay. Then you have a similar set for W2. For this E2 is a subset of S. So these EIs are subsets of S. Okay. And for you are getting an EI for each WI. And now you are taking the unions of all this up to EM. Okay. Yes. EIs are finite sets. Okay, because what is S? S is a spanning set of V. Okay. And what does it mean? That every element of V is a finite linear combination of the elements of S. Okay. So for every element here, you are getting a finite set of elements here. Of course, there could be other elements in S of which WI is also a linear combination, but you are taking some linear combination for which you can write this equality. Okay. And there exist finitely many elements in S for which you can write this. I mean, some finite set of elements. Take that in your E1 or EI. Mahfuz? Finite linear combinations, of course. Yes. Exactly. Yeah. Yeah. What if we don't know a finite spanning set? What we are trying to do, we are trying to reduce a spanning set of a finite dimensional vector space to a basis. We will consider, well, as you mentioned, we'll come back to that. We'll say what happens in an infinite dimensional case. But now we are having a finite dimensional vector space. Okay, and a finite dimensional vector space means that you have a finite spanning set. So your S is that finite spanning set. Okay, but you are now given an arbitrary spanning set. You want to reduce it to a basis. So how you go from S, I mean, at first you must reduce S to a finite set and then use the algorithm that we talked about in the last class, okay? Beforehand, the omegas? No, it's an existential proof. There's a difference between these two. I mean, we are not constructing a basis here. We are just saying that a finite set of subset of S will do. That is, there exists a finite subset of S which will span the entire set V. So this W1 to Wm, you know that there exists some W1 to Wm. Okay? Yes, Nitish. Yeah, but suppose you were given some arbitrary infinite subset of V, okay, that is spanning V, and then you are asked to reduce it to basis. How do you proceed? It may not be if you do not start with a finite set, then the question is that how do we reduce this to a finite set, okay, a basis? Mani? It's a yes. Yeah, so in for example, consider R3, that is I mean, where the points have x, y, z3 coordinates, right? And yes. So suppose you take a plane in R3. Suppose you take the xy plane and take one of the vectors in z, one of the vectors which have not z coordinate 0. Okay? The question is that whether that will contain a basis. Okay? It does contain a basis because that will span the entire set, the xy plane and some vector with a non-zero z coordinate. Okay? So suppose you are in such a situation, okay, Nitish, and then what you are trying to do is, well, from the plane you try to get two linearly independent vectors which combined with this vector with non-zero z coordinate will give you the basis. Okay. Okay. So we are doing that in general. How do we proceed? Okay. So this is how you are going to proceed. You are going to write each of the vectors in the finite spanning set as a linear combination of the vectors in S, and then you have a finite set of vectors. I mean, linear combination of the elements of this are expressing each of these elements here. Okay. And what does it mean? If you call this set as, say, S dash, what property does this S dash have? Yeah. Exactly. It's finite, it's a subset of S, and it spans V, because this one spans V. Okay. And since every element of V is a finite, well, it's a linear combination of this is a finite set. So it's a linear combination of these elements, and since every element of that set is a linear combination of this set, S dash, that means every element of V is a linear combination of this set, S dash. Okay. Yes, Mahfuz. S dash, it can be. I mean, we do not know whether S is finite. We said that we do not know anything about its cardinality. Okay. Yeah. So now we are in the previous case. We are having a finite spanning set, and now we are trying to reduce it to a basis, and then we just discard elements which are belonging to the span of the other elements. Okay. So we just proceed as we did earlier, using the lemma that lemma or proposition, whatever we have written that. So proposition proved in the last class, that is span of SV is equal to span of S if and only if V is in span of S. Okay. So we keep on repeating this on this set and throw away elements. So we take some, I mean, this is a finite set, right? We pick one element at random from that and check whether that is in the span of the other elements. If it is, if yes, we throw it away. If no, we keep it. Okay. And we have to perform only finitely many checks. Okay. And we are done. All right. And suppose the set you finally have obtained, that's not a basis. Can it happen that it's not a basis? So you are checking every time whether the element that you, so it's a finite set, you order them in, it's a finite set, you can order it in any manner, and check the first one. Is it in the span of the rest? Yes, throw it away. No, keep it. Go to the second element. Okay. Is it in the span of the rest? Do the same thing. Okay. So finally, with this algorithm, since it's a finite set, someone is sleeping. You remind me the greatest teaching of Rowling: a sleeping dragon should never be tickled. So, yeah, what I wanted to say is that, yeah, Trishit, then perhaps you can tell this. I mean, whether this whether this algorithm is finally giving you a basis or not. You are choosing one element from here, checking whether it's in the span of the rest. It's a finite set, right? Throwing it away if it is. If not, you keep it. Go on. Okay. So finally, you are having a set of elements such that none of its elements are belonging to the span of the rest. Is that a linearly independent set? Somebody said yes. Okay, but let Trishit answer first. So the question is that if you have a set let S be a set such that none of its elements are in the span of the other elements. of its other elements. Is S linearly independent? I mean, we are in such a situation, we are claiming that that's the basis. But if it is a basis, it should be linearly independent, right? So, I mean, at the end of the algorithm, we have such a set. The question is whether the elements of this set are linearly independent. Why? Yes. Which one again?
You try to write one element as, let's say it is not linearly independent, then you can write it in as a linear combination of others.
Right, very good. So suppose S is not, okay? So answer, if not, then there exists V in S such that V is a linear combination of the other elements, say A1, V1, AI, Vi, sorry, I running from 1 to n, and all these Vi's are elements of S as well, okay? Now this one will give you, wait a minute, excuse me. If it is, well, excuse me, sorry. If it is not linearly independent, well, we would like such a relation, okay? I mean, if we could write it, then we can say that V is in the span, we can throw V away, okay? But we, at this, I mean, at the given scenario, we cannot write V in this manner. But if there exists a linear, I mean, if these are not linearly independent, then there exists some linear relation among them, okay? Then there exists Ci in F such that summation Ci Vi I running from 1 to n for some n is equal to 0, and not all Ci's are equal to 0, and this all these Vi's are elements of S, okay? So then in S there should exist such a linear relation, and that would contradict the fact that these are, I mean, none of the elements are in the span of the others, because if not all these Ci's are 0, there is at least one Ci which is non-zero. Take it to the other side, okay? This is the trick we have done several times now. So if, say, Cj, some j, is not equal to 0, that would imply that minus Cj Vj is a sum over this Ci Vi in the original set such that I is not equal to j, okay? Divide by this Cj, minus Cj, and you get that Vj is then summation minus, sorry, is equal to minus summation Ci by Cj Vi I not equal to j. So Vj is in the span of all the Vi's such that I not equal to j, and that is giving us a contradiction, because we said that S is a set such that none of its elements are in the span of the others, okay? So indeed such a thing should be linearly independent, okay? So we are getting a basis indeed, okay? Now the opposite thing, that is, if you are, so we see that given a set S which is spanning the vector space, be the set spanning a finite dimensional vector space, be the set finite or infinite, we can always reduce it to a basis, okay? Now the opposite scenario, that is, we are having a linearly independent set, okay? You recall in the first class or the second class we were talking about a vector space coming to you with a with a broken basis, and then you slowly extend it and say whether it's painful. So it is this one, okay? A linearly independent set, you can think of it as a broken basis. You are trying to extend it to a full basis, okay? So this is the proposition. Let L be a linearly independent subset of a vector space V. Okay. Then we can extend. Then L can be extended to a basis of V by adjoining elements subset of, well, still we are in a finite dimensional condition. So finite dimensional situation, sorry. So suppose L is a linearly independent subset of a finite dimensional vector space V, okay? And L can be extended to a basis of V by adjoining elements V in V to L successively, such that, I mean, one after another, such that LV is still linearly independent. Okay. In other words, what we are trying to say, maybe we write it here. Well, even before writing it clearly here, we must recall what is a linearly independent set. What's your name, please? Yeah? Gayatri. Gayatri, what is a linearly independent set? What is a linearly independent subset of vector space V? We just trying to recall the definition. Linearly independent subset of a vector space V. So what is this? Right. Except the trivial linear relation, there are no other linear relation. Okay. But here again, you are talking about a finite set. And suppose now we are forget about that finite dimension for the moment. Okay. Suppose you are in a general vector space, say vector space of functions. Okay. Functions from R to R. And suppose you are considering a linearly independent subset of that. So how do you define a linearly independent subset there? It's a set S in V such that the only finite linear combination of its elements which yields 0 is the trivial relation. Is a trivial linear relation where all the coefficients are 0. That is where all the coefficients are 0. So a general set is linearly independent if there exists any, I mean, if you have that any finite subset of it having some linear relation, that relation should be trivial. If that is true, then we set the general set to be linearly independent. And now, what we are trying to do, we are trying to extend a set L to a basis of V. Okay, and well, this step is simple, but we'll not cover it in today's class. I think we did it in the last class. Well, actually, we can recall it just. Then we can say what happens in general in the next class. I mean, in general, for a finite dimensional vector space. So Abhijit asked last time whether a basis exists or not, and we said that it follows from John's lemma, but we won't go into it. We can say a little bit, like for 5 minutes, we can spend 5 minutes more on that. But let's recall at first what happens in this case, that is what we did in the last class. Okay, so you have a linear. In the last class, we started with a finite set. Okay, so L was some V1 to Vn, and we said that we would adjoin one element V in V to L and construct L dash as L comma V, and then this would be linearly independent if and only if V is not in the span of L. So L dash defined in that manner is linearly independent if and only if V is not in the span of L. Okay, and we didn't prove it directly. We proved so this was the proof. We proved the contrapositive, that is L prime is linearly dependent if and only if V is in the span of L. Okay. Now suppose we start from here. V is in the span of L. So we start from here. Say that means V is equal to summation Ci Vi I running from 1 to n. That implies then, well, this is if and only if summation Ci Vi I running from 1 to n minus V is equal to 0. That is giving you a linear relation, okay, with not all the coefficients 0, because this coefficient is -1. So that means this is if and only if, well, at least that implies, okay, that L dash is linearly dependent. Okay, there exists some relation. Now, if there exists some relation in L dash like this, well, not like this, maybe we just write it down here. C1 V1 plus C2 V2 plus dot 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 plus Cn Vn plus Cn plus 1 V, that is equal to 0. Suppose L prime is linearly dependent now. Okay? L prime linearly dependent. We are trying to show that V is in span of L. Okay? And that means, can this be 0, Cn plus 1? If it is 0, that would force this one to be equal to 0, the rest of this to be 0. But you know that none of this coefficient can be 0, because V1 to Vn were in the original L, which is linearly independent. Okay? So Cn plus 1 must not be 0. Okay? That implies V is equal to minus C1 by Cn plus 1. So you can divide by Cn plus 1. That is, you can multiply with the inverse of Cn plus 1, multiplicative inverse of Cn plus 1. Okay? C2 by Cn plus 1 V2 dot 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 minus Cn by Cn plus 1 Vn. Okay? V is equal to this, and that means V is in the span of L. Okay? So we started with this assumption first, that V is in the span of L. We have shown that L prime is linearly dependent. Now we started with L prime linearly dependent, and we have shown that V should be in the span of L. So indeed, we have the proof of this proposition, that L prime is linearly dependent if and only if V is in the span of L. So we apply this one repeatedly to obtain a maximal linearly independent set for a finite dimensional case. Okay? What happens in the infinite dimensional case, We'll see in the next class.